Hi, welcome back. So what I'm going to do is continue our studies in simple harmonic motion. What we left off in the previous lecture video is that I was talking about the conditions for the period of a spring. So let's take a quick peek at these. So these are the conditions to measure the period of the spring. And as I said before, this is really nice because you don't have to take a time measurement to do this. It's based on the system, so based on the mass and the strength of your spring. So the cool part about this, I think this is really neat, is that the period does not depend on how far you pull it back, the amplitude. It's actually quite strange, so I want to demonstrate that this is in fact true. So, what I'm going to do, as long as the system's the same, right? So I'm going to use spring 1, the same spring, the same mass. And in the first case, I'm going to pull it back 40 centimeters. So I'm going to do that, and I'm going to let it... I'm going to take friction off because naturally that will affect your system. So we take friction off, and what I'm going to do is pull it back to the 40, right in the middle right there, and allow it to go ahead and do our period. So I'm going to take it from the 40 and then back to the 40. So here we go. So 0.63. Okay, so let's stop this and let's go to the 50 now. I changed the amplitude to 20 centimeters instead of 10. Let's let it oscillate. Let's reset and start at the 50. And look at that. So very close. Of course, it's not exact because I'm not really good at the timing, or at least not super good. But you can see more or less the amplitude actually doesn't matter. Now, it looks faster because notice that we had to pull it more. It has more force. So it can actually go back to where it has to be in the same amount of time because it's directly proportional to the force that we pull. So I think that's really cool. Let's go ahead and stop this. There we go. Roughly right there. So another thing you need to know about the system, and I'll do some sample calculations in the following videos, is to understand the conditions of our system. What happens when the spring goes through the equilibrium position, this line right here? What happens at the extremes, at the negative amplitude and at the positive amplitude? So what we're going to look at is where does the maximum velocity occur, the zero velocity occur, maximum potential, and kinetic energies. So let's start off with the horizontal spring, and honestly, the horizontal spring is the same as the vertical spring system. So if you can see this diagram, and I'll just move me out of the way for a second. There we go. So I'm over here. You can see this is modeling a spring, right? So let's pull the spring back, and we know that it will go this way, as you can see here, and then come back. So let's talk about what we see here. So at the very end of the spring, okay, what you're going to have is the spring will actually stop. And I'll show you an example of this too. So right here at the maximum amplitude, so this is your amplitude, right? The velocity here is going to be 0. Now if you think about it, I'll show you too, is at this point the object stops. Now notice we also have a stretch here. Like that, max. So the force of a spring is labeled as negative kx. Negative just means it's going to do the opposite of what you do to it. So if you pull it, it's going to be pushed. So don't get too worried about that negative sign, but more importantly, notice that we're going to have a force because we stretched it here. So we have the maximum force at A, the amplitude. And then we're also, because the force is directly proportional to acceleration, we're going to have maximum acceleration at AX. Like that. So at the stretched point, so this is our stretched point, you're going to have the following conditions. So notice at the equilibrium position right here, and actually before I get back to this, notice that our energy is going to be elastic potential energy at that point. So we're going to have 1/2 kx squared. So we're going to have our maximum energy there. So we have our most energy at this point in terms of elastic potential. Now the kinetic energy at this point, as you might imagine, will be 0 because we have no velocity. It's not going to move. And this is at the extreme point, so right here. And this is at the extreme too, so the max point right here. So the most kinetic, the most elastic potential, no kinetic, etc. Let's go to this case. Right at the equilibrium position, x is going to be 0 because that's where we take our stretch measurement. So if x is 0, it means we have no force, right? Because it doesn't matter, negative k times x is 0. So we have no force here because the spring is at its equilibrium. It's not being stretched or compressed at that point. But it does mean that we're going to have our most velocity because all the kinetic right here, all the potential right here will go into the kinetic. So what we have at this point, right at the equilibrium position, is we have maximum kinetic, no elastic, we have no acceleration because we have no force, and we have our maximum velocity at that point. So as you can see, this is symmetric. So over here, it's going to be the same case as this right here. But if you're doing technically, although we usually just take an absolute value, this is technically a negative sign because it's on the opposite side right there. So don't get too caught up in negative signs. It actually reflects this exact situation. And then I'll call it situation A. And then of course this one is the exact identical to this. And it's periodic. So, and you could see that too in the spring system right here, is that if I pull this down and allow it to oscillate, that it stops at the very end, so it stops there and stops here, so the velocity is 0, and you get the most velocity right in the center right here. And you can see it here in the energy system, right? So if I pause this at the extreme, let me try this. Try my best. It's not actually at the extreme, but you can see all the potential energy there. A little bit of the kinetic always equals to the total, right? And then if I could try again, I'm going to try to pause it right in the middle. This is hard. Okay, let's try again. Oh, not bad. Not great either. Because I still have some elastic potential energy there. So you can see that I'm a little off. But ideally, you can see that I have more kinetic at that point. Now, this comes from the fact that it is hanging. So that's the extra. So that's a gravitational part. But in this case, let's just look at the elastic. That's what we're talking about here. All right, so we can solve for some of these conditions pretty naturally. So I like to look at energy in this system. So remember, energy is always conserved. So if we look at the extreme cases, the endpoints, and the middle point, we can say that all the potential energy at this point has to go into the velocity at this point. And remember when I talked about earlier, we do have zero kinetic energy here, and then max kinetic energy here, max potential energy here, 0 potential energy. So we can set these two equal to each other. So this is really helpful. In fact, you'll actually see that X max is sometimes labeled as A, and I think I have that in my later slide. So it's a really good technique to solving this. So if you have somewhere else that's in the middle here, right? So you can have something like this. Oops, sorry. So say the equilibrium position's right here. And let's say that the max position, X max, is here. So you have a position in the middle. So what you're going to have is you're going to have some velocity here and some X. So if we want to know the energy at this point, we have to add up the two types of energy. So we have the kinetic and the potential. And then we could always set it to the total energy of the system. So if we know something like the max, we can do 1/2 Kx max. We could do something like this. So this is helpful, or you could do the opposite if you know the other condition. If you know the velocity max, you could do this. So that will give you any information you need in the middle point, so the midpoint like this. So you can look at this diagram on your own. It's kind of talking about exactly what we talked about earlier. And same thing here. This is just the plot of what we just discussed. So as you might imagine, at some of our extreme cases, you can see that when you're perfectly stretched, so this is a max case, your acceleration, so your velocity is 0, as it should be, and your acceleration, since you're stretched, is at maxed. So this is at the stretched. The equilibrium position is right here. That's where it's 0. And you can see the same condition. So you have roughly your max velocity here. And then what you're going to see is roughly, kind of didn't draw it straight, but it should be here, a 0 acceleration, like that. And we just kind of talked about this. So the filly's in. At max compression, your position's at max. Your velocity is 0. Your acceleration's max. At equilibrium position, your position's 0. Velocity's max. Acceleration's max. 0, sorry. So you can see that they're the exact inverse of the two. So what we can do is to solve for the acceleration of the system. So if you look at this, when we're at so let's say this is the equilibrium position, when we're here, the force that is going to be acted on this mass is going to be the spring, because the spring's going to want to pull it back. So if we want to know how fast it pulls back, we could set this equal to the definition of a force, which is ma. Now the force of the spring is kx. We can set it to ma, so kx over m can give us the acceleration of our system. Once again, don't worry about the negative sign too much, but it just means that if the object's going down, the spring's going to pull back up. It does the opposite there. So we're going to get this max at x max, and I hope that makes sense, because if x has a value, then you'll have an acceleration. When x doesn't have a value, like 0, you will not have an acceleration. Okay, so what I'll do is I'll reserve the next couple of videos to do some of these out on, so you can see how everything plays together with the equation. So the biggest things is looking at the energy perspective of this, looking at how to calculate the period using m over k, and then of course looking at the conditions, the extreme conditions, whether it's a graph or you have it like a diagram like this. So the next videos I'll solve some spring problems.